college, pharmacy college. I was there for a very short period of time. Then I left to NCL Pune. So I do have very fond memories of my colleagues over there, the then colleagues over there. Some of them are still there, and I really remember them very fondly. Anyways, going forward, I did come, yes, I think in 2018, I did visit and I had given a talk in that. So ever since then, we have been focusing more on metrology and biosensors. And today I'll be talking on two of my best publications of this year, which is on metrology and biosensors. So I'll be taking two different research that were conducted in the previous year and which resulted in high impact journal publications. So I'll be discussing and sharing my experience in that aspect. For those who are seeing me for the first time, and just to give them a brief introduction about where I come from, on where I am, and what my institution is all about. So I'll be talking about that. See, University of KwaZulu-Natal is one of the premier universities in South Africa, and it does have a world ranking within 500 top universities in the world. So please don't be under the impression that anything in Africa or South Africa is very what do you say, backward country or anything of that sort. Like, no, the South Africa at least is a very quite well developed nation with world class facilities and so on. So is the university. Like, so it is one of the biggest university in Africa, and it is a research led university. And we have 5 campuses. We are on Westville campus, where I'm based at. This is the Westville campus. And then we have this Pietermaritzburg campus. And Pietermaritzburg campus is a Pietermaritzburg place where Mahatma Gandhi was actually thrown out of the train. And that's where he started his fight against discrimination and from colonialism, fight against colonialism, sorry. And then this is the Nelson Mandela School of Medicine, which is a very famous medical school in South Africa. And this is the Howard campus, and this is your Edgewood campus. So Edgewood campus is mostly deals with all arts and so on. Howard campus is mostly engineering. This is medicine, and Maritzburg and Westville campuses are mostly dealing with sciences, basic sciences. So it's 5 big campuses. We have somewhere approximately around 8 to 10,000 students and 3,000 faculties and so on. Anyways, going for that was a brief introduction. I always start my talk anywhere, wherever I give my talk in the world, the 2 greatest humans or souls that walked on this earth were these 2 people. And I'm fortunate that I'm an Indian, so Mahatma Gandhi and Nelson Mandela, where I'm presently living in here in South Africa. Like, it is ever becoming more important we as human beings to know more about these 2 great humans and their teachings. It is becoming ever more, their teachings are becoming ever more important especially for the younger generations and also everyone across the world, across globally. They are global leaders. And we are proud that they were part of, they were from the same nations where we are in now. So I just pay my homage to them every time I start my talk or wherever I go for lecturing overseas and all, like, anyways. So going back where I come from, this is South Africa, the southernmost part of Africa, and here is where I'm based at. Sorry, I'm based here in Durban, and this is Maritzburg, just 100 kilometers. And these are the Drakensberg Mountain, sorry. And then this is your Kruger National Park. So you should always remember, like whenever you see Discovery Channel, or National Geographic and all, when you see all the wild animals and the tiger, the lions and all types of big fives and all, it is in Africa basically, and especially South Africa and Kruger National Park. And we have two landlocked countries here. If you look here, this is the Lesotho and Swaziland. These are the two landlocked countries within Africa, South Africa. And here is your Cape Town, where you see the Table Mountain. So this is the, we have different provinces: Northern Cape, Eastern Cape, Free State, Northwest, Limpopo and all. So this is where we are, South Africa. And South Africa is basically surrounded by two oceans, as Indian Ocean and Atlantic Ocean. So basically I'm based here in Durban, on the coastal area. So going forward, this is my campus where I come from, in the Westville campus. It's called as Westville campus, and it is on the top of a mountain basically. And you can see that there's a typical South Africa, like an African continent, where it is on a nature reserve. Everywhere else is a nature reserve. So sometimes when it is very quiet, especially now during the COVID situation, when the campus is very quiet, you will see some deer, or you'll see some animals basically walking around when it is very quiet on the roads and so on. And so it's a beautiful campus, what I can say on pitch of this one. And if you are on this campus, you can actually see throughout the Durban. And from my house, presently where I'm sitting now, from my window, I can actually see my campus. Anyways, so that is where I come from. You'd see my labs are located in the swastik kind of building. This side is my lab, where the Synthetic and Medicinal Chemistry Research Group is located. Okay, what I do, basically mine is as a pharmaceutical chemist, but my PhD is in organic chemistry. So I moved in over there, and then over the years, I've also opened up into nanoscience applications. So the target-based drug design is one of the core focus areas, and I work on designing new molecules for TB and your cancers. In cancers, I work on different, basically kinase family, targeting the kinase family, whether it is CDK or spindle kinase, EG5 or KSP, so on. And in antimicrobial agents, basically focusing on TB, I work on lactate dehydrogenase, DNA gyrase, and diethyl reductase enzyme. And also, we have also started working on acyl ACP reductase enzyme. We recently published one article on that as well. So, in methodology, my aim is more focused on developing small molecules or APIs or those scaffolds of pharmacological importance, whether natural or synthetic scaffolds of pharmacological importance, by using cheap chemicals, available chemicals. And that is what I'm going to talk about today, where even if you do not have sophisticated instruments, you just have some glasswares and a heating mantle or a stirrer, you can basically do wonders. Like, in the sense, you can synthesize very beautiful molecules, cheap molecules. And biosensors, it came across to me as when this lady you see here on top, on my left side, was my initial group in 2013 when I started my research group. So I just want to introduce her. She's Dr. Neeta Thapliyal. And she joined from IIT Roorkee. She came over here and she joined my research group, and that is when I started working on biosensors. And that is Shivanandan Karunanidhi. He is now with NIT Kochi. He's Cochin NIT. He's a faculty there. Is Balakumar Chandrasekharan. He's also a faculty member now. He is Francis. He joined me from UK and he's back in his country as a faculty. Girish Hampan now, he joined Cayley College of Pharmacy. He's an assistant professor there. And he is Srinivas Cherukupalli, who joined me, and he is now graduated. All of them have graduated. The PhDs and the postdocs have gone, and they're doing very well in their life. In fact, everyone who graduated, that is what I feel more proud about. That people who graduated from my research group are well placed and doing very well in their life. Anyways, going further, this is a brief introduction of what we do, what SMCRG does at UKZN, and so on. Okay. So what I'm going to speak about in today's lecture is about on methodology and the biosensors, which has taken more priority. I wouldn't say more priority, like we have been publishing a little bit more and high impact journals, and our success is more so on that. And especially this year, even though the labs were shut down and everything, we took some special permission, and we did complete some work, and that resulted in, and it was worthwhile because it resulted in some very good publication. So the first what I'm going to say, talk about is a methodology, and we all know 1,4-benzoxazine, okay, component, a heterocyclic component, a very versatile heterocycle, oxygen nitrogen containing heterocycle, which is present in many marketed drugs as well. So what I'm today is basically, this paper was recently in just 2 months back, it was published in Journal of Organic Chemistry, and the topic was basically 1-part multi-component diastereoselective green synthesis of the dihydro 1,4-benzoxazine analogs. So I'm going to talk about this and a little bit story about this, how we approached. And the second thing I'm going to speak about is on biosensors, on MRSA detection, methicillin SRS detection of this the pathogenic bacteria, the seriously pathogenic bacteria. Okay, so going forward, we all know 1,4-benzoxazine, a versatile heterocyclic scaffold, and has a wide range of applications. It is present as a core molecule in many pharmaceutical drugs, from antibacterial to your anti-diabetic, arithmetic, and so on. Like, there are several drugs which have this as a core scaffold, and one of them is levofloxacin. If you look into levofloxacin, also it does have a 1,4-benzoxazine scaffold, and levofloxacin is also a 5th or 6th generation antibiotic. So it is a very important scaffold. And while doing some work on, previously when we had published a work on in EJOS, European Journal of Medicinal Chemistry, in 2018, we were also on quinozolones, we published some papers. So we had this interest on this bicyclic nitrogen and oxygen containing molecules, scaffolds, which we can synthesize moieties which can be further exploited as building blocks. Going further, like, these are some examples, like, levofloxacin, you can see this, the core moiety over here, levofloxacin. Then you can see your azaceratron, basically a serotonin 3 antagonist. It also has a benzoxazine moiety. Then you have bemrodin, a vasodilator agent. Then you have your potassium channel activator, and so on. So these are some of the and also in agrochemicals, you have your herbicide as thiodiamazine, and flumazoxin, the herbicides, and where you see this as a benzoxazine as a core moiety, based on which different molecules are synthesized, or active molecules are synthesized. So how did this start? Like, we were actually looking into some literature, and basically what we do is whenever a PhD student joins me, then I ask, we discuss on topics, and then we start, I also take into consideration what he or she wants to work on. And then we decide on a topic, and then the first thing they do is, once the topic is decided, is to write a review article. So you will also see that we also keep on writing a lot of review articles. Every student has to write a review article before he or she starts actually doing the bench work, or starts the PhD work or master's work. So what happens is that this literature review gives them the in-depth knowledge about that particular field. So one of the students joined in 2017, and that is how we were working on at that time benzoxazides, trying to develop new molecules based on benzoxazine scaffold. And then he took up this project and he started doing. So while doing literature and all, then we came up that this, like previously reported methods. So if you look into the previously reported methods, what was done while doing the literature, we did find some gap, because when you write a literature review, you do come, you first thing is you get a vast knowledge about that particular field, what has been done. The second thing you get is by reading all those research articles, like 50, 60, 100 articles in that area, you will also come to know that what is the gap that you can address. That is how you can get a problem for your PhD, like problem statement for your PhD, which you need to solve. So this is how we came about. We wanted to use basically do a scaffold hopping on one of the anti-tubercular drug, and we wanted to do an isosteric replacement. So we were looking into how about using the benzoxazines, and that is how this whole thing started. So if you look into the previous literature, like what people, the way they have synthesized different building blocks or benzoxazines, also differently substituted benzoxazines, is that they commonly use your aminophenols, and the aminophenols, then they treat them with the different reagents and in the presence of like extremely sometimes toxic and sometimes expensive catalyst to get the benzoxazine scaffold. So in 1996, what they had used is, one of this is like aminophenols, and they had used alpha halogenacyl bromides, and they use the base, and this is a two-step reactions using your boron hydride as a catalyst, as a base, and then cyclization and getting your benzoxazine. Then in the same year, they use nitrophenol, orthonitrophenol, and then they use the same haloesters by reductive cyclization using granule and hydrogen gas, and got the benzoxazine. Now, in 2009, these are some of the important like advances in synthesis of your benzoxazine moieties that I'm putting it over here. So in 2009, there was a report in tetrahedron letters where they used the intramolecular copper catalyzed over-rylation of beta amino alcohols. So they had this iodoamine, and then they used the substituted oxiranes and the intermediate, and by using copper iodide and phenolphthalein as catalyst and copper iodide and dioxane solvent and so on, they did this cyclize this product, obtain the substituted benzoxazines. Similarly, if you look into other, in 2003, they were same, like they used the fluorinated substituted tosylated amine and then oxiranes and halosulfonamides and so on, and then they got this. So these are some of the reported methods. The latest was in 2018 was the latest, where they used the 3,4-diheto 1,4 benzoxazine derivatives by using Weil-Lewis acid catalyzed SN2 type ring opening and activated azidyl with the 2-halophenol, okay, and in the presence of copper iodide catalyzed reactions. So these are some of the literatures what we found. So based on this, we wanted to see that how, by using common chemicals, like common chemicals and reagents that we use, you will be very surprised. Like we use such simple techniques that any one of you in your lab can actually synthesize different molecules. And as we go on in this talk, you'll see that. Okay. So what are the limitations? What did we say? As I said, when you do a thorough literature search, you'll get all this point. What is the limit? The finding out the gap that we can address. Okay. So most of these reactions were multi-step. Okay, and that is at least 2 steps or 3 steps in reaction, and they used bases and they used expensive catalysts, hazardous solvents. They used ligands and other additives they used, and then their low yield, they suffered from low yields, long reaction time, and they did not have distereoselectivity. They lacked stereoselectiveness. And they were building the blocks. The final product were not versatile enough to exploit them as in building blocks. Like they had their own limitations. So this was, then we came up with something very simple. So in our present approach, first thing is our approach is completely catalyst free. It doesn't have any catalyst. We use very common solvent, that is ethanol, which is very environmentally friendly and not so, it's a green solvent, falls under green solvent. And it's a very green approach. We had 1 pot. Right? You dump all this and you just use 7 hours and you will be 6-7 hours and you will be done. Then mild conditions, you use basically mild basic conditions, like we use your this one. And then what you're getting is a distereoselective, like you can get one enantiomer, distereoisomer as more yield, like of almost 92%, and sometimes it is distereoselectivity is 99%, 99:1, and you have wide substrate scope. So this was a far more advanced than so far reported. So what we are doing is we are taking aminophenol and we are taking different aldehydes like aliphatic to alicyclic to aryl substituted, non-substituted aldehydes, and then we are treating them with your phenacyl bromides basically. And what you're using is ethanol. Then you use your mild base K2CO3, and all these things are commonly available in your lab. In most of the labs, they are commonly available. And see, if you look into, we also got the crystal structures through which we proved the stereoselectiveness of the compound, like the cis and trans distereoselective compounds. So 9A and 9B. So I'll be explaining this more. And if you look here, especially the trans and cis configuration was basically it was proved through both X-ray crystallography and through our NMR analysis. We did prove that the molecule existed in cis and trans. You got 2 distereoisomers. Okay. So basically looking at this H8 and H7 protons, like in this is a trans with respect to the substituents over here, and similarly this is in cis with respect to the substituent on the molecule, if you look into that. Okay, so going further, like what would we do? So our approach, the advantages, it is non-hazardous, like the hazardous solvent-free. Basically, we are not using any, in fact, not using any much solvent. It is mild base, commonly K2CO3 or potassium carbonate is readily available in the lab. It does not have any metal-free. It is completely metal-free, catalyst and ligand-free. Okay, economical, very economical, one-step, multi-component, qualitative and quantitative approach means you get very good yield and you get in high purity. Okay, and mild reaction conditions, easy isolation, and distereoselective means you get, if you control the reaction, you get one stereoselective and distereoisomer in a better yield. Okay, So these were the advantages of our work. So what did we do? Like if you look into look into this reaction, so we just took a heating mantle, we dumped all those reactions like phenacyl bromides, amino alcohols, and aldehydes, and we dumped it and we added some. We stirred it for 1 hour with um, in ethanol, and then we dumped the K2CO3 and reacted them for 7 hours. And then you will get basically, I'm taking one of the molecules 9A and B to show you the diastereoselectiveness of this. So what we did the reaction, you can see the TLC is very clean. It is after 7 hours, the TLC is very clean. You're getting 2 spots here, okay? And we identified them 2 diastereoisomers, that is cis and trans. So 9A and 9B basically, okay? So if you look into the crude NMR, if you isolate this as a crude product, you'll see that in the entire NMR, you'll see that when you take a mixture of diastereo mixture of NMR of a diastereo mixture of compound, then you'll basically get all doublet, like, signals in the NMR, like, you can see all this. So you can see adjacent number of signals because of the 2 stereoisomers present. So we were easily, now these, any chemist can easily separate when the RF values are so different, they can easily separate these 2 molecules. And that is how we isolated them. And then you can look into, this is expanded version of this region, the fingerprint region for the diastereomers, like 9A and 9B, the peaks appearing at different resonance. And these are the pure isolated NMRs of that. So we got one of 9B as a highest like yield, like diastereoselectivity, and it was basically your trans molecule. Okay, so but the cis molecule we were unable to isolate it because the yield was very less, because it was diastereoselective synthesis. So how did we optimize this reaction conditions? Like, optimization of these conditions. Like, we took simple reaction. We wanted to optimize, like what conditions, how much to use, what, and also on. So we did base screening, we did solvent screening, then we did temperature screening and time screening and so on. So we needed to come at an ideal temperature, ideal solvent, ideal base, and ideal time, like at what time you can have the maximum yield, and after that no more further reaction takes place. So we started with some basically commonly available chemicals in our lab, in any lab. So sodium carbonate, sodium bicarbonate, potassium carbonate, cesium carbonate, sodium hydroxide, triethylamine, diisopropylethylamine, sodium bicarbonate, and so on. So initially, what we observed is, you'll see in the previously reported methods, most of the people are actually using expensive bases and their hazardous solvents, and the reaction times are almost 24 hours or maybe more, or 20 hours or 16 hours time at high temperature like 120 degrees, and so the yields are also very low. So what we did is, initially we did the base screening, and what we did is we replaced that base with commonly available bases in our lab. So we took sodium carbonate and we took DMF solvent, and then reaction time was 5 hours and 120 degrees. You could see that the yield was 43. Now going further, we changed into a little bit more stronger base of K2CO3 in DMF, and then we maintain the time as such, we maintain the solvent, and we maintain the temperature. The yield slightly increased to 47%. Okay. Then we kept the base constant, and then we changed the solvent from DMF, because DMF is not a good solvent for, especially for workup, and this it is very difficult to isolate and do the workup of DMF. Reaction is quite difficult, and it is a little bit messy as well. And what we were also observing in these 1-2 conditions was that the reaction was quite messy. Even though we did get 40 or 50% yield, but the reaction was quite messy. So when we used ethanol, the reaction was not that messy. We kept the same, and we also slightly lowered the temperature at 90 degrees, and we got a better yield, like 56%. So what we thought is that, okay, K2CO3 is a good base, ethanol is a good solvent. Let's look into the time and temperature now. So we just reduced kept the time the same, but we reduced the temperature, and it increased. So then we thought that why don't we? So what we are doing is we are keeping the time constant, but as we're reducing the temperature, we are seeing that the yield is increasing by keeping the base and solvent constant. So what we did is basically we put the same reaction at room temperature, and you could get, and we said, oh wow, we got 91% yield, and that too with the diastereoselective compound. So 91% yield. So this was our best. So we also screened other bases and solvents and all. So the best we could get was this. Then the second was using your cesium carbonate base and same time and temperature, and ethanol. So at room temperature. Imagine somebody doing it at 120 degrees Celsius. Now we have come to room temperature. Somebody doing the reaction at 40, like the 24 hours or 20 hours or 16 hours. Now it has been reduced to 7 hours. Solvent is just a common solvent, ethanol, and a common base, basically, a very mild common base. So this is how. So we could not still believe. So we confirmed this through our NOSI spectra, 2D NMR spectroscopy. This is NOSI spectra. For NOSI spectra is which tells you about through space correlation, proton-proton correlation in a molecule. So this is the NOSI spectra, and an expanded version. If you look into the protons over here, so NOSI basically what it does is you can see through space proton correlation, like proton of this proton can see any proton when they come in through space, and they come in close proximity. So now if you look into the NH proton over here, 4, this is showing NOSI correlation with 3, the adjacent proton, and also with the 3. But then if you look into the 3 is showing NOSI correlation with both 2 and 4, and it is also showing correlation with your 4 and 2 protons. Like, so this confirms that this molecule is this is a major diastereomer, that is a cis diastereomer is formed by basically based on the conformation. So NOSI correlation gives you basically 3-dimensional conformation of a molecule or orientation of the molecule. Okay, it gives. So through this it was confirmed as a cis diastereomer. Okay, so cis diastereoselective, which was obtained at 1.5 base equivalent, and ethanol, and temperature at room temperature. Okay, so this we got, and the reaction was carried out at 2 ml solvent, and the diastereometric ratio of the compound 4 was from proton at 2 proton NMR was used to determine the yield of that. We also did the isolated yield, and it was 5:1. Okay, was greater than 5:1. So we synthesized using this, we wanted to look into substrate scope, like how well we can exploit this methodology to build different types of molecules, known or unknown, or novel molecules or unknown molecules, and how well this method can be exploited. So what we did is we kept the phenacyl bromide constant, and we used different aldehydes. So we took different aldehydes, substituted aldehydes, then aliphatic aldehydes, and then just aliphatic aldehydes, and we took substituted aromatic aldehydes and hetero cyclic aldehydes and so on. If you look into over here, and we were getting excellent yields and also diastereoselectivity. These are the different substrates. What we like scope of substrate scope was investigated, and we could see right over here we synthesized somewhere around 20 odd compounds, or more than that, and we were able to get very good yield and activity. Going further, what we did is basically the same. Here we synthesize all these molecules, and we also investigated using, okay, coming here, like one of the drawbacks, what I can say about my own work over here, which are still investigating, is that you cannot carry out this reaction in the absence of like aliphatic bromine. That is, you need a phenacyl bromide, aromatic phenacyl bromides, okay, aryl bromides. So you cannot do it with aliphatic bromides, okay. So that is one of the drawback of this, and we could use any substituents over here. So that was one of the versatility. So if you look into the mechanism of action, we all know how the skiff base forms. So it is basically initial formation is a skiff base. That is, you have an aldehyde and there's a nucleophilic attack onto the carbonyl carbon, and it leads to the formation of a skiff base. And then this intermediate 5 acts as a nucleophile and attacks. There's a bromine as a good leaving group. The simultaneous take place an SN2 mechanism. You get this intermediate 7, and intermediate 7 again, the base basically abstracts this proton, activates this oxygen, and leads to the generation of an intermolecule intermediate, unstable intermediate, and leads to the generation of a carbon anion, which further leads to the cyclization, activation and cyclization of this compound. So this is the proposed mechanism of that we proposed in this work. So going further, like these were some of our proton and representative proton NMR of our compounds. So you have the aromatic protons and the NH proton you can see over here, and the methoxy, which was used as an indicator. Okay, so going further, if you look into COSY correlation, now COSY, we confirmed this with confirmed the molecule with COSY, because initially to grow a crystal, we did not get the crystals immediately. We had to actually grow the crystals to prove our the cis and trans configuration, to authentically prove our cis and trans configuration. But however, prior to that, we use the 2D NMR techniques like, your NOSY, COSY, HMBC, HSQC experiments, where NMR experiments were done to prove the confirmation of the formation and the confirmation of the desired product. Okay, so here in the COSY correlation, if you study this, COSY correlation means only you can see the adjacent protons. In the COSY correlation, you can see adjacent protons like attached to the carbons. Like, so important, if you look into the 3H over here, it will show the COSY correlation with the NH, and it will show the COSY correlation with the 2H. Okay, so if you look into this here, 3H proton here, it is showing the COSY correlation with the 2, and it is showing the COSY correlation with, it is showing, okay, the 3 is basically showing the COSY correlation with the 2, and also the COSY correlation with the 2 and 4. Okay, so you look here at the 4 here. So the 3, the proton 3 is showing COSY correlation with 4 and with 2. So that is significant. Okay, that is one of the authentication. And then if you look into the 2 is only showing COSY correlation with 3, and the 4, the proton 4, the nitrogen proton 4 is only showing COSY correlation with 3. So adjacent proton. So that confirms that, these are some of the important aspects that confirms that these are the desired product is formed, like it is 1,4-benzoxime. Okay, So going further, if you look into your HSQC and HMBC, HSQC is carbon to proton correlations. It just tells you which carbon is attached to which proton and so on. But HMBC is a vital experiment which tells you about mostly about alpha correlation between alpha protons. For example, if this is your methoxy proton, that 15 methoxy proton here. Now, if you look into the 3H, that is this 3H, there's 3 carbon 3, it shows HMBC correlation with 2. Also, it shows HMBC correlation with 12, that is here. Okay, proton of the 12H. So this carbon 3 is showing HMBC correlation with 12, and it is showing HMBC correlation with 2. Okay, and then if you look into the carbon 2, it is only showing HMBC correlation with 2 is showing with basically your 13H. 2 is showing to your to your 3, and it is showing to your basically no, it is only showing it to 3. Okay, the carbon 2. So another important correlation what we observe in HMBC is your carbon 14. Now carbon 14 is, this is the carbon 14 or 15 is showing the carbon 14 is showing the HMBC correlation with 15, and it is showing HMBC correlation with 12 as well as 13. Okay, you can see this here, HMBC correlation. And the 16, carbon 16 is showing, that is this carbon 16, carbonyl carbon 16 is showing HMBC correlation with 3 and HMBC correlation with 18. So this proving the entire molecule. Of course, as we go into this core structure, it becomes much more complicated to do it, but you are observing all the correlation, required correlation to justify the formation of this compound. Okay, so the main correlations are your 14C carbon, 16C carbon, 3C and 2C carbons. Okay, so this proved the structure of the compound. So in conclusion, what I would say is that we have developed efficient one-pot multi-component green catalyst-free and diastereoselectric synthesis of 1,4-benzoxazine in excellent yields. We have got 91% yield diastereoselectivity. Okay. Then reaction was proceeds in situ formation of a skiff base, followed by base-mediated O-alkylation with the phenacyl bromide, and finally catalyst-free intermolecular cyclization. Then you have new versatile methodology. It's a new wide scope. It can be exploited to build as a building block. And then you have different functionally substituted benzoxazine scaffold, which can be further exploited. Okay. So we are looking into some other new molecules, or designing these new molecules based on this scaffolds and all. So this was one of the publications of this year, one of the best publications of this year, and you would see that the reaction conditions and all what were used were very mild and green, basically. Okay. Anyways, so this is one of the part what I wanted to talk about, the methodology. And with the given era, like the methodology is becoming extremely important in trying to discover environmentally friendly methods for the synthesis of APIs, basically. Okay, environmentally and low cost, environmentally free methods. So that is one. So my second topic is on biosensors, which I'm talking about. And this work was published in Sensors and Actuators B, impact factor somewhere around 7 or 8 impact factor, I think so. And it is one of the top journals in sensors. Okay. So this work was done here, and most of the work was done here in our laboratory, everything. And what we did here is that, to give you a little bit background, we know that one of the biggest problem of treatment and management of any disease is it not being detected early. We do not have any early detection techniques for a particular bacteria or a particular pathogen and all, like, you know, whether it is TB or whether it is your protozoal infections or whether it is bacterial infections and all. It has to go through laboratory techniques, which takes 1 day, 2 days, or a week to get a result, and so on. Okay, we don't get that. So time becomes very crucial, and usually initially a symptomatic treatment is given, and most of the times we are pumped with if you go into any doctors or physicians, not all I'm saying, but in general, they prescribe you antibiotics, which might be more, your infection might be a gram-negative bacteria, but then you're giving an antibiotic which is more specific to gram-positive bacteria or something of that sort. So the proper management does not take place, or diagnosis does not happen, and you are given with basically the doctor prescribes you a broad spectrum antibiotic and all, like, you know. So one of the important aspects of management of a disease is early diagnosis. Like, you know, even if the results are not very conclusive or authentic, but at least you get an early diagnosis, like, okay, this is what it is. So that is a technology that I wanted to investigate on in developing sensors. So some of the very well-known sensors, what we have, chemical sensors, what we have is your people who are suffering from diabetes, they use your diabetic glucometer, like, you know, they just put a drop of blood on their strip and then they measure the blood glucose level, and that is basically an electrochemical sensor. And then you have your pregnancy test, where you just drop a urine and you just come to know your this one. And now you are having for different, even for some cancers also, you have certain test protocols for knowing what cancer it is and at what stage it is, and also on. So, but we don't have for diseases like malaria and bacteria, common diseases like bacteria, we do not have that, what particular bacterial infection we are having, okay? So that is what is interesting. One of the most commonly infection basically spreads through your hospital infection or community-borne infection and so on, okay? So one of the biggest problems what South Africa faces is your MRSA, like, you know, Staphylococcus aureus, not just South Africa, but all developing countries, developed countries, is hospital-acquired methicillin-resistant S. aureus infection, okay? And it is very dangerous. Once you have this resistant strain, then it is very difficult to treat, and especially with your pre-existing conditions, the morbidity is very high, like especially in patients with immune-compromised patients, especially those patients are with age-related ailments and so on. So what do we do? Like, you know, how does we all know how the resistance comes, antibiotic resistance happens, and it becomes very difficult to treat the resistance, okay? So beta-lactamase is one of the enzymes that is responsible for causing resistance. I will not go much in detail in this aspect, okay? So we all know about that. So mode of transmission this is the mode of transmission. Like if you are an infected person and then you go to the hospital and then you basically, somebody comes in contact with you and with this one, and the hospital gets infected, or you may get it via hospital itself when you're admitted into the hospital, or the infected person walks into the community, then it transmits into to other people and into your livestock and so on, okay? So these are the different mode of transmission of MRSA, methicillin-resistant S. aureus, okay? Then early detection of MRSA is very important, and there are some existing methods, but they are not very conclusive at all, okay? So our interest was this, to develop MRSA detection, okay? So we have different traditional traditional ways where we take the urine sample, or we take a blood sample, or urine sample, or feces we take, and we do the culturing of that, and then we look into the strains, and then we stain them, and then we come to know like what basically bacteria they are. Then there are some using of MRSA biomarkers. We use certain biomarkers, certain proteins or enzymes that are expressed more during the infection time, or and they're specific to that particular pathogen. So you have luminance-based detection, then you have PCR-based detection. Now PCR-based detection is also used for your COVID-19. Okay, we do not have any spontaneous detection kit for COVID-19. When you give, they take the swab, and then they go and then they do a PCR, and the results are coming after sometimes a week, or maybe sometimes 2 or 3 days, and it's too late by that time. Sometimes it's too late. And then there are some novel techniques. So what I am facing, what I am more interested, or my lab is more interested, is in developing electrochemical detections, because these are most widely available. And the market value of these sensors is currently, if I can speculate, is somewhere around $14 billion per annum, the world market of this. So if you get a simple and very substantial qualitative technique, then this basically becomes a very good, a direct application. It can develop a product basically. Okay, so early diagnosis helps in better treatment and point treatment basically, and biomarkers, identifying a novel biomarker, or this one a particular biomarker helps in detecting a particular pathogen, and for early detection as well. Okay, so these are different methods and techniques. So what is a brief overview of how is that? So electrochemical sensors, what is it? Has an annulate. That annulates are things that we want to detect. It can be a pathogen. It can be, say, heavy metals like lead, arsenic, and all in water polluted, or pesticides, or explosives as well, or gases. It can be particular gases like poisonous gases and all. So the sensors are everywhere. You go into a home, you have a sensor like smoke sensors. We are all surrounded by sensors, including you're driving a car, your car has particular sensors. The way if your battery fails, the way it starts beeping. If you're not wearing the seat, there is a sensor, and so on. Like this, we are all these days surrounded by sensors. Okay, it is just that we are not aware of it. So I'm more interested as a health practitioner. I'm more interested in pathogens, like early detection of pathogens. But you can also apply for all these heavy metals, pesticides, and all. So bioreceptors are those molecules, or macromolecules, or molecules that are biomolecules, or it can be material that basically act as receptors. That is where the annulate comes and binds. Okay, it can be antibodies, enzymes, aptamers, or it can be any other material. Okay, any other macromolecule or biomolecule, or any other surface. Okay, modified surface. Now, transducers are that surface on which the bioreceptors are immobilized, or put onto it, and we use different materials, conducting materials, like we use mostly graphene, carbon nanotubes, reduced graphene oxide, and so on. Okay, so transducers basically enhances the conductivity of this one. So what we get out of this is, when we apply a potential, what we get out of this is a current, potential, resistance, and so we get an electrical response. So we basically measure this electrical response based on there can be an increase in electrical response, or there can be decrease in electrical response. So we use cyclic voltammetric techniques, which can detect this one. I will take the questions once I have finished my talk. Okay, once I'm finished, you can have all the. I'll have some time, and I can actually answer all the questions. Okay, I know some of the people are raising their hands. So, anyways, so going further from here, yeah. So this is a brief diagram of electrochemical biosensors, the components of the electrochemical biosensors. Okay, so components of our component of for MRSA detection was your annulate was your MRSA cells, your bioreceptor was your vancomycin drug. Okay, and then transducer was a copper nanocomposite material basically, and I'm going to talk about in detail about all these materials. And then we had a differential pulse voltammogram through which we detected the detected our fabrication or detected the MRSA. Okay, so the annulate was MRSA cells, the bioreceptor was vancomycin, which is a drug basically, and the transducer was your copper nanocomposite material. Okay, so how did we do this? So what we did is basically we use a hydrothermal approach. So we used the synthesis was done by using your copper nitrate salt, and we took the beta cyclodextrine, and we basically to the beta cyclodextrine, and then we use hydrothermal apparatus under pressure, and we heated it for 115 degrees Celsius, and then we got your beta cyclodextrine with copper nanoparticles, and then we added your reduced graphene oxide to immobilize this onto this. So you will see that we had different sizes of copper metal. Now, copper as such is an antimicrobial. We know that in our traditional ways, like if you go into your old houses, into the villages and all where we grew up, or most of your parents grew up and all, we still use, and it has become very fashionable now that it has come into back that we try to drink, we try to store water in copper and so on. Okay, so copper is very it has an anti-microbial property, and what we observed is the larger size copper particles, they acted as larger size nanoparticles of the copper acted as better, improved the conductivity and also the antibacterial activities. Okay, so some of them, the copper particles were trapped inside the cyclodextrine, and some were the larger particles were immobilized on the graphene oxide. Okay, so this larger particles basically enhance the conductivity as well as the antimicrobial property of the composite material, and the cyclodextrine acted as a guest host, like in the sense in actually the larger copper materials were helpful in detecting or binding to the binding to the bacteria basically. Okay, so that is what how this was the complete overview of how the composite material was synthesized. So this showed the 3D nanocomposite was synthesized, which showed a high electrochemical conductivity and ease of bioconjugation. Now, bioconjugation is basically we had reduced graphene oxide had this hydroxyl groups, and we know that as a medicinal chemist or pharmaceutical chemist or an organic chemist, to the hydroxy group, you can basically, they become handles for immobilizing other biomolecules or macromolecules or a drug molecule on them, because it is easy to, hydroxyl groups acts as hydrogen bond acceptors or help in hydrogen bonding, as well as having entrapping certain metal molecules as well. Okay, so characterization, how it was done, I would look into this. We conducted an FTIR when we used initially we used the copper and beta cyclodextrine. That is what is your basically your the black contours graph, and beta cyclodextrine with reduced graphene oxide. So that is your red. So it shows it was, so the IR was quite conclusive that we got a complex of beta cyclodextrine, copper, beta cyclodextrine and graphene oxide. So through FTIR. Then we used the SEM So another important thing what we observed is that this at a particular concentrate ratios of the material. For example, you have your SEM. We found a porous material. So all this what you see is basically is your copper nanoparticles, and what you see is over here is the porous material of your graphene and beta cyclodextrin. Okay, porous material. Then with HR10 transmission electron microscope at 50 nanometer, what we observed is this material is a hard material and it is an intact material. It is not a scattered or broken material. So these were very crucial. And when we did the BET to do the surface analysis, so we almost had a 70% increase in surface when we did the relative under relative pressure and based on the absorbed the quantity absorbed. Okay, so the surface was increased with graphene oxide. Okay, BET. So going further, the electron EIS spectrum, it shows that if you look over here, just copper and beta cyclodextrin, that is your black, you'll see that it has a better conductivity. But with vancomycin, beta cyclodextrin, and your reduced graphene oxide composite material has a better conductivity. Like you will see here, there's a reduced better conductivity. Okay. So going further, this was your cyclic voltammogram, and you'll see that basically cyclic voltammogram is basically you apply potential difference across. When you apply the potential on this, then you will see different voltammograms. Like blue stands for just bare GC, that is bare glassy carbon electrode, and red is your,
for time being is fine.
Oh, okay. I'll just finish very quickly. Like, okay, the bare is your with your copper and beta cyclodextrin and glassy carbon electrode, modified electrode, and you could see that the conductivity has increased. And then you will see the black slightly reduced, but you can see that. Okay, so this is beta cyclodextrin with glassy carbon electrode. So the red, which is this, with the entire composite material, it showed a better conductivity and diagram. So bioreceptors, vancomycin was used as a bioreceptor to capture MRSA. Then with the help of EDC and NHS and N-hydroxysuccinamide and ethylene, EDC is a coupling reagent used in peptides and all. We immobilized that, and vancomycin basically binds to the D-alanine amino acid of this bacterial cell wall, and that is how it. So this was our idea and composite to do that. Okay, and this whole thing was immobilized on the graphene oxide. So these were characterized. I'm not going to go in detail. I know I'm short of time, but what I can say is, how do you determine the concentration of vancomycin that has to be immobilized? So we increased the concentration at 1.2 millimolar concentration on the surface concentration. We could see that there was no more increase in detection or something of that increase in, so it fell. So this was ideal concentration was 1.2 that needed to be immobilized on the surface. So going further, detection mechanism, what we did is, this is a bare GC electrode, and we used the beta cyclodextrin, copper and beta cyclodextrin and glassy carbon electrode that was coated on the bare GC. On the bare GC is vancomycin, and on the vancomycin, through your coupling reagents, we immobilized the vancomycin, and the vancomycin detected the specific MRSA. And for methicillin-resistant SRES, vancomycin is the only drug, last resort, to treat it. Okay, so this copper itself act as an basically copper inactivation. So this is how the detection limit, what you see over here, as the gram-positive bacteria MRSA is attaching to it, basically what is happening is the sensitivity is reducing, and that shows that that our experiment was successful. So incubation time, concentration studies, and calibration plot were all done. I'm not going to go in much in detail. So range of sensor was 10 to the power 7 CFU per ml, and then loading capacity was 5 CFU per ml. Okay, antibacterial property. If you look into this, this shows the antibacterial property. One thing I want to conclude to you guys, and also to all the pharmacists and young students. We were doing something else, detection, but now we have come up with something else, and ongoing research is going on. This composite material is as equipotent as the vancomycin itself, or more. Now, what do you conclude from this? Is that this, if used as an external application for treating a skin infection or any material, disinfecting the material, or having a material which is resistant to MRSA and all, we can apply this type of material, this kind of composite material on these materials, and composite material on that surface to make it as antimicrobial resistant. Okay. So that is, in conclusion, we developed through pi stacking a beta cyclodextrin and glycine carbon oxide, leading to high surface area. And one of the drawback of this was, I'll also say that one of the drawback is that once you have modified this, once you have made this electrode, it's a single-use electrode. You cannot use it again and again. One use and throw. Okay. So we have also done this work on screen-fitted electrodes as well. Okay. So we could, from 8.8 microgram, the MIC value was from 8.8 microgram to 1.93 microgram was observed due to the presence of copper nanocomposite material, that is the antibacterial activity. So the two people who worked on this was on JOC, Nardeshwar Kushwa and Dr. Atal. Both of, he has just submitted his PhD thesis, and he just graduated. He's graduating in September, basically. So these are the two people who did this wonderful work. And my research group in 2015, this was my research group. And 2017, this was my research group. Presently, this is my research group. So we have people from all over Africa and some from Europe as well. Some of them are missing. It's a big research group of 25 postgraduates with 4 or 5 postdocs and so on. So we are one of the most vibrant research group in UKZN and in South Africa as well. So this is our what I can say, 2019 and 2020. Now recently some more students have joined for PhD. Okay. So in conclusion, my acknowledgements first to my SMCRG group. I always like to acknowledge them because it is because of their hard work that we are able to do good science and their dedication on the bench, and that is what is keeping the SMCRG group flying in and the university flying. And I also like to thank the university, Danan Sagar College of Pharmacy and Danan University for giving me this opportunity. My university, Nanotechnology Platform, CHPC, and NRF RSA. And opportunities, just brief, they are PhD, postdoc opportunities, sometimes funded, which you can contact me directly for if you need any opportunities and all, then we can talk over that. But selection procedure is very, very tough selection procedure. So thank you very much, and my apologies for running over the time. Thank you.
Thank you, Professor Rajshekhar Karbamat. It was a very good session, particularly after a long time we are hearing about the synthesis and characterization of heterocyclic compounds, particularly on anti-cancers. Now, I have a question. Can I go ahead, Rajshekhar?
Yes, please. Yeah.
Regarding the stereochemistry,
yeah.
How do you know the proportion, like whether dextro is 60, levo is 40, or the vice versa? During the synthesis, how you are going to characterize that the final compound is 60% of the levo and 40% of the dextro?
Okay, one is through, you can do it by your crude NMR, looking at the peak integration. Okay, that is one way. The second way is through your isolation of the compound itself, because we were able to isolate it. if I showed you the TLC also, both the diastereomers 9A, 9B, and several compounds were isolated. In some compounds, there was specific diastereoselectivity that only a particular diastereoisomers was synthesized in more quantity, and only trace amount of other was synthesized. And that is how we proved the percentage. But most of it was done by NMR, peak integration.
Okay. Now by using the column, will you be
Yeah.
able to separate this D and L? If it is case, if it is say yes, how long it will take to do the separation?
See, it is cis and trans. Yes, you can separate them. Now, I'm not talking about D and L, but cis and trans, you can separate them. See, here it is, and as I said, they're distinct, and it was pretty straightforward. They were quite not non-polar, but by using a proper solvent phase, we were able to separate them in quite in pure quantity, basically. In fact, I would say that the methodology was so simple and easy that, in fact, the compound used to precipitate out of the solvent. After 7 hours, you could see the precipitation coming out. So it was sometimes we didn't need to synthesize, need to even do the separations, because we almost got 1:99% stereoselectivity, 99:1 ratio, and we hardly needed any separation. What I mean to see is one of the diastereomer actually precipitated out, and other remained in the solvent. So that was another way it was easy for us, and that is why this methodology is so simple and was so promising and important. Yeah.
Yeah. Thank you, Professor Rajshekhar.
Yeah.
Sir, there are few questions from the audience side.
Yes.
So one question is like the limitations of green chemistry technique. What are the limitations of green chemistry techniques? What is being used?
Green chemistry is very difficult. I mean to say, like, not everything happens in green. And green, we always misunderstand. Like these days, even using DMS for small quantities called green, but green is not. Actually, green is something using less harsh conditions for the environment. Not all reactions go in water or in ethanol and methanol, and by using waste, you need some time. Harsh. You need sometimes a special catalyst for activation and so on. The other thing, one of the things that I can give you, which everybody should explore, is your solar chemistry. What we use the sunlight to do most of the reactions, basically. In nature, basically, most of the molecules are synthesized by using the solar energy in your water, or where water becomes one of the major solvent. But this is a hot topic now and is being done elsewhere. But yes, green chemistry, we do have a lot of limitations. Not everything is possible to synthesize through that, and that is how we use this. Because if you look into here, we have moved from DMF to ethanol, which I don't say as good as water, but it is just good enough. Like, yeah, we do have limitations, yes, and that's why when you do a green synthesis, you come out with simple green techniques. I assure you, either you can patent those things or you can publish them into high impact journals.
Thank you very much, sir, for addressing the question. Another question is there. It says like, how does biosensors role? I mean, what is the role of biosensors in defense?
In defense, as I said, that biosensors are present everywhere. Everywhere as I'm sitting over here, as I'm using my laptop, my phone, everything these days comes with sensors. Now, with the warfare, now you know that chemical warfare is one of the worst kind of chemical warfare, and what is that? Biological warfare. Yes, chemical warfare and biological warfare are much more devastating than, especially the biological warfare is much more devastating than weapons like weapons of just give if I give a layman comparison, uh, just say a bomb falls somewhere, God forbid it does not happen, it never happens, but falls somewhere and it destroys, it kills around 100,000 people or 1 lakh people in that particular city, and the entire city is destroyed. If you have a pathogenic warfare, like you have a mutated and lab synthesized pathogen, deadly pathogen, and you put it in human chain or in animal chain, and it comes into the human contact and it spreads, and you don't have a cure, you pump the element, and that is what I'm not saying anything. I'm not pinpointing at anything. Look at COVID-19, the entire world. It is, you can call it as a, I don't want to blame a country or anything. Let's not go get into that. But biological warfare can be so difficult, and there where comes your sensors, like to detect a particular pathogen or a virus or a bacteria or a fungus or something, a wide application, or a particular chemical agent like nerve gas, for example. We have nerve gas, and we also have for gas leakages, like even in your home also, smoke sensors, gas leakages, and hazardous gas leakages. For example, Bhopal gas tragedy, one of the worst gas tragedies in the world, which killed thousands and thousands of lakhs of people when they were sleeping. So then hydrogen cyanide gas. So these all where we need sensors, where, and especially those places where the humans cannot venture, you need sensors to see to be there. Like so sensors are there everywhere. So there are thermal, electrical, luminescence, and all those kinds of sensors. And so biological warfare also is it has wide applications. Yes.
Okay. I don't think there are any more questions from the audience side. So we have come to the end of the session. On behalf of the management and staff of DSU, my heartfelt thanks and appreciation to the speaker of the day, Dr. Rajshekhar Karpurmat, for accepting our invitation to this webinar and sharing his valuable thoughts and findings on this important area of chemical sciences. I would like to thank Mohammad Imtiaz, Mr. Saikat Ali, Mrs. Deepa, and Hemant for their support in organizing this webinar. I would like to thank our Dean, management, and faculty, and all the participants of this webinar for making it successful. Thank you all. Thank you once again.
Thank you, everyone. Thank you once again, Professor Murugan and Professor Kalpana Devakar, and all the students who are there and who are actually attended the. So you can always contact me for anything on the work that has been presented and so on. Thank you very much for this opportunity. Thank you.
Thank you, sir. The feedback forms are posted in the chat box. Kindly fill the form today itself and submit so that you will receive your e-certificates. Thank you once again.
Okay, fine. Thank you.